Okay. Good evening. So, since there will be no one else here, we'll start our discussion session and the problem solving session mainly. So, here we are actually going to discuss about the Mossbauer spectroscopy, how it actually works, and what kind of nuclei actually active for the Mossbauer spectroscopy. Basically, right now we are going to discuss something about the theory part, and then we'll have some question depending on your weekly assignments, and you can go through with that and solve those assignments, and then we'll come back to then and in the next week, and then we'll discuss about the what is the problem you found, what is the answer you expect to, and what you got, and we'll discuss about those things. Okay, and then I've gone through all the questions. I found the question is super easy, so you can if you go through this lecture, you will definitely find answer on your uh, on your assignments. And then there's some tricky question over there also, so you can easily solve it after this kind of uh, doubt solving section. Okay, so last Saturday we actually discussed about introduce about the Mossbauer spectroscopy, how my Mossbauer spectroscopy works with the help of the absorbing gamma ray, and my nucleus state has to change to a different nuclear state. So in that case, we are providing huge amount of energy, and that energy actually absorbed by my nucleus and getting excited and giving me the spectroscopy with respect to their absorbance. Okay, and there is the different spectroscopy we are talking about, not it's similar absorbance spectroscopy, absorbance UVB spectroscopy, or my IS spectroscopy. Here we are actually providing huge energy that is called gamma ray. We are using gamma ray. Now question is the what is the source of the gamma ray? But the gamma ray source of the gamma ray is not as usual our sodium lamp or deuterium lamp or halogen lamp or any radio. In an in NMR we are providing the radio wave. This is energy, the gamma ray energy around 10 to the power 10 to the power more than 10 to the power 4 electron volt. It's a huge energy, and that energy actually provided by a similar kind of nucleus. Okay, and that nucleus actually providing me the gamma ray, which is actually as similar to my samples, and then we'll able to provide that energy which we are looking for. Okay, so we actually discussed about that. We have one of my source over here. Let's suppose we are talking about this is my energy axis. We have I equals to, let's suppose we have a ground state is I equals to half, and we have I equals to 3 by 2 energy state, and then we'll have the state over here. We are providing energy, decay of the energy we are getting, and then providing its decay its energy to as a gamma ray, and that ray actually absorbed by my sample. This is source, and we have my sample over here. It's supposed to be similar in energy, otherwise it cannot absorb this light. and this my energy observed. This is I equals to half and I equals to 3 by 2. Okay, and then this energy has to be absorbed by my sample. Okay, it sounds to be very simple, but it's not. We have some problem about it. Okay, first of all, our major problem is source. Source, what are will be the my source? Second point is it's the energy gap between source and sample. Energy gap source and sample should be similar. Okay. Otherwise, she cannot absorb the my gamma ray. Okay. So another major problem here we are actually getting a huge amount of energy. It has a some recoiling effect. Okay, let's suppose we have a gun. We are providing huge amount of energy inside the bullet. Bullet is going in a speed of around 10 12,000 kilometer per hour. To provide that amount of energy into the bullet, they actually backfire backfire, push you to backfire, and that is called recoiling. We have a huge amount of energy, that is gamma ray. We are talking about gamma ray. It's a very huge amount of energy, and that gamma ray actually going forward, it has a backward effect, that is called recoiling. And due to that recoiling, my some energy actually lost. Let's suppose we have a sample. Let's suppose here we have some sample over here, source. This is the source. We have a source while the providing the gamma ray, decaying the gamma ray, it has some recoiling effect, that is called recoil energy. Recoil energy actually puts back my nuclei. Okay, and then it's it lost its energy, whatever we are expecting. So let's suppose we have an energy around this amount of energy we have. This is energy axis we are talking about. Let's suppose we can do it in a next page. Okay, we have a something called over here. No, we have energy. We have a I equals to 3 by 2 and I equals to half, 2 straight over here, and we have this is the decay we are talking about. This is the energy gap between I equals to half and I equals to 3 by 2. but there is some recoiling over here, and the energy which is actually providing, this is called E transition, this is E gamma, and there is one term recoiling energy is called energy, which is called as a my E of R, and here supposed to be my E transition will be my E will be my E of gamma ray, sorry, E of my gamma ray plus E of my recoiling energy. We can rearrange it that E of gamma ray equals to E transition, can write it here, minus E of my recoiling energy. Similarly, let's suppose we have a bullet. Suppose I'm wearing a bulletproof jacket. Okay, it's a huge amount of energy which is stored into the bullet. As a momentum, bullet is coming towards me and hit my bulletproof jacket onto my bulletproof jacket. It somehow make a mark on the bullet onto my bulletproof jacket, and they will push backwards towards the direction of my bullet. So that is also a one kind of recoiling energy we are losing. So we have a sample, huge amount of energy, but energy is coming, and that is the energy which is actually sample over there. It actually pushing back towards the direction of my traveling of my gamma ray. Okay, so there also we are actually losing some energy. So for that we have the gamma ray over here, which is actually coming out of it, and we have a similar energy state like I equals to 3 by 2 here. Okay, we can write over here I equals to 3 by 2, and I equals to half over here. This gamma ray actually coming, and that is absorbed by my gamma ray, absorbed by my this is source, and this is my sample. Okay, and here also we are actually getting some called, this is ETR gamma ray. What is the gamma ray? Oops. Energy of gamma ray, which is equals to be my E of transition plus E of my recoiling energy. So that means we have a gamma ray which is actually higher than my E transition because of the recoiling energy needed to absorb, to match my ground state to excited state of my sample. That should be higher in energy, otherwise it cannot absorb. Okay, so here of course these two equation we are getting from the source. We need the gamma ray, which is actually we will get the actual E transition minus the recoiling energy, and for the sample the gamma ray is requires actual transition energy, plus we need a recoiling energy for the sample. So we can we can easily plot it with respect to the energy and the absorbance. Let's suppose this in a let's think about it. We have a axis, y axis. We have energy axis over here. Somehow it should be a term of the energy. We have absorbance over here. If my source be like this, and this is my transition we are talking about. Okay. Okay. This is the transition or the ETR. This is the ETR we are talking about, and due to the record we are getting, this is ER. This also ER. We are losing some energy because of the recoil, and we don't get any source and that much of overlay. So it is a very poor resonance we can get. Here we can get very poor resonance, and which is actually very poor due to the poor overlap between source and my sample of source and sample energy. Okay, so now what is the solution should be to that? The one scientist who has been actually developed some technique, which is the scientist is named as Rudolf Mossbauer, and by his name this spectroscopy has been done, and he got the Nobel Prize because of this development of this beautiful technique. And this phenomena has been well known for previously, but no one can actually think about this way where the Mossbauer actually did these things. In the Mossbauer, Rudolf Mossbauer, during his PhD, he recorded a phenomena. He started to look the this phenomena within a source and sample in a particular way that people are actually using, and then he started the lowering down the temperature, and he is getting some scope. See, he is getting some data. A very good overlap has been found between the source absorbance versus energy curve and the sample absorbance and energy graph. They found a very good overlap. And to check that phenomena, he thought that why this phenomena is happening. Maybe there is in the low temperature there is something which is actually making this overlap recalling energy less recalling energy during the low temperature, lowering down the temperature. And he make another beautiful experiment where the sample the he make a lattice where my source will be there, and also he made another lattice for the sample. That means my source and sample are in solid phase. Okay, so we have a, we have a sample in a solid matrix, and we have a source in a solid matrix, and he recorded that there is a very good overlap between this source energy graph and the sample energy graph. And he found there is some good result to absorb my gamma ray, which is actually decay from my source. Okay, so Mossbauer, what he did, he actually make source in a matrix form. That's how we are. I'm writing this way because of that. This is actually hooked in a solid. Okay, we have a source, and also so in a solid matrix we have a sample. Okay, a sample, we have a show. This is source and this is sample. And he found this gamma ray, which is actually decay, kind of similar energy, but the samples is required. Okay, this here he found another thing, interesting thing. This recoiling energy actually made of two kind of energy. One is the translation energy, uh, trans. We can write it. We initially write it transition, so we can write it E translation. And plus E of vibration. Okay, that is the this energy because of the lattice vibration. Until and unless we can make a absolute zero temperature, this lattice vibration always be there. So it may be less number of lattice vibration, but it's supposed to be there. Okay, and by making the solid matrix, he is cutting off the E translation energy. Okay, and this E vibration, which can be written as, sorry, now we can cut it later on. This is the E translation plus this term can be written as a vibration energy U in H bar I. This is the frequency of vibration. Frequency of vibration, and this is the n equals to what, the n equals to 0 1 ground state, 1 2 3 etc. 0 is the ground state, first excited state, second excited state, so on and so forth. That is what is found in the vibration spectroscopy. You can find it this kind of in turn. Okay, by making the lattice we can cut down, this is actually 0, and right now this energy actually found enough as a phonons, and n equals to 0. These phonons can be cut down by the lowering the temperature. We can minimize this phonon because of this vibration energy actually decay by the phonon. Phonon is nothing but a heat we are getting from the lattice vibration. By lowering down temperature, we can l- minimize the this vibration, this lattice vibration. Lowering down the temperature can minimize the lattice vibration. Okay, and this is where this er, now er becomes 0, and that is called recoilless transition. Okay, recoilless transition. Okay, now we can say that recoilless transition is a required for the Mossbauer spectroscopy. But we will not get that recoilless transition because of the we are not going as absolute zero. Until and unless absolute zero, there should be a lattice vibration, and that lattice vibration is actually responsible for the some recoil energy, and we lost the some recoil energy, and then instead making this low temperature at the low temperature and the solid matrix, the absorbance and energy graph becomes right now like this will be my observance, this will be my observance, this will be energy parameter, and here will be your source, and we can change the color. We have sample over here. Sorry for my bad drawing. We'll get a very good overlap over here. Okay, and this is my the transition, actual transition energy over here, and this is because of the recoil, recoil because of the lattice vibration. Here we can get a better overlap, and very good resolution. Okay, now can I make a very highly line broadening or sharpening by this observance? Why is this? So there is some energy over. If we make a recoilless energy, a recoilless transition, then it should be my sharp line. Here comes a Heisenberg uncertainty principle into the picture. The Heisenberg uncertainty principle, let's suppose we have a transition called I equals to 3 by 2 to I equals to half. Heisenberg uncertainty principle, line which, depending on the line width, is a major factor coming to the picture. Line width. We have some picture over here that is, sorry, Here is the I equals to 3 by 2, I equals to half, and we have this transition over here. And here comes the Heisenberg uncertainty principle. Line with this is called the half maxima of the my transition. This is called line width. Line width. Line width, which is a line width is gamma. This is capital gamma. And in the Heisenberg uncertainty principle, we have a similar parameter, something like called delta x. X is a position, and delta this is the momentum, which should be h cross by 2. We cannot measure the position and the momentum simultaneously. Okay, so if my delta x infinity, then my delta p becomes 0. Otherwise, we will get the line broadening. Similarly, another kind of term we can get, that is called delta energy. Delta energy, the energy, and the delta t, that should be h cross by t. This is the similar kind of energy we are getting. Similar parameter we are similar to the my parameter we are getting from the Heisenberg uncertainty principle. If my delta t tends to 0, then my energy should be infinity. Otherwise, so the lifetime of this is the lifetime. The lifetime of excited state is not going to be absolute 0. There should be some value, and energy that we have is some energy. Otherwise, energy will be infinity. Otherwise, if my delta t is infinity, energy should be 0. So in the obvious case is that there is some value of delta t and there's some value of the delta e. And here we can say delta t cannot be equals to 0. And then we'll, if 0, then delta e should be my infinity. It cannot be possible. Now we have some value of the delta t, we will get the line broadening. Okay, so here the term is delta e into delta t is greater than equals to h cross by 2, and this delta e can be lined with this energy can be written as delta e can be written as my line broadening by 2, and then we can write it gamma by 2 cross delta t equals to h cross by 2, which implies delta t greater or equals h cross by gamma. This is the term we are getting. Okay, h cross by gamma. Now our major discussion is the iron. We are going to talk about the majorly the iron. So for the iron example is the iron. Here we have the iron which is actually Mossbauer active. In the iron we can say sorry. Oh my god. What happened? Just a minute, hold on guys. There is some technical issue in my computer. Just a minute. Okay, welcome back. Sorry about my another device. So where we are taking an example of the iron Fe57 and this is my 26. For that here the I equals to transition will be my I equals to 3 by 2 to I equals to half, and for that we have lifetime of that 3 by 2 I value, the iron 57 I value of 3 by 2 lifetime will be my delta T, which is actually 141 nanosecond. And then as we know, delta T equals to H cross by gamma, or gamma, okay, sorry, greater or equals, or gamma greater or equals to H cross by delta T. For that we can say gamma equals to, we can put all the value, we'll get 5 into 5.0 into 10 to the power minus 9 eV, and resolution of the spectra can be written by gamma by E value, and which is actually 3.3 into 10 to the power minus 13 ev. As this value, the energy of this transition is equals to 114.3 14.4 kilo electron volt for this transition E3 by 2 to E by energy gap between two state of I equals to 3 by 2 to I equals to half. Okay, so here we can compare the what is the energy gap between so we can say that this is my resolution, which is actually very lesser than my optical spectrum. Okay, so we can compare with the optical spectra with the resolution with the help of the resolution value and the energy gap optical spectra. And here we can write Mossbauer. Mossbauer spectra. Here are all the parameters. Oh god, the gamma value, which is around 10 to the minus 8 order. This gamma value around 10 to the minus 9 order. It's kind of similar, nearly similar. Energy is huge difference. Energy is 0.121 electron volt, which is actually 10 to the power 4 order. And gamma by E value, which is the resolution of the spectra, which is nearly equals to 10 to the power minus 7 to 10 to the power minus 9 order. And for this we have 10 to the minus 13 order. So this is less resolved spectra than optical spectra. Okay, so it is already by default is a very less result spectra. Now another problem is now there will be another problem because of the isotopic abundant. Okay, now question will be what are the major isotope we can detect by the Mossbauer spectroscopy. So for that we have another list over here. You can check. We can go through the Google. Okay, so let's make it bigger. Okay. Okay. So it is there. It's not moving. So all the white colored one, this is called iron, potassium, cesium, technetium, ruthenium, zinc, gallium, krypton, xenon, iodine, tellurium, antimony, tin, and all the lanthanums, cadmium, tellurium, tungsten, rhenium, osmium, iridium, platinum, gold, mercury, barium, and some actinides called thorium, polonium, uranium, neptunium, plutonium, aluminum. All those are active in Mossbauer spectrum. But some of them we are not actually going to measure that because of their unavailability of their similar isotopes and similar kind of energy source we don't have, then we cannot measure their mass spectra. Majorly we actually you focusing on the iron because it is a very well established chemistry of the iron in biology. We had know that our hemoglobin, myoglobin, all are made of lots of enzymes which are made of the iron, and to detect their redox property, their geometrical property, which can be used, which is actually this redox property can be detected by the mass spectroscopy. So people widely use this iron mass spectroscopy uh, to detect the iron and its geometric change, its oxidation state change, and spin state. All those things has been changed can has been actually observed by this mass spectroscopy. Okay, so to that we have some isotopes. Those are those majorly monitored by the Mossbauer element, major element. Wrong thing. Major elements detect major elements monitored by the Mossbauer filter is which is actually mainly the iron Fe57 isotope, my tin 119, and antimony 121, iodine 129, gold 197 isotope are majorly used for that. Iron is the major major part. One iron 57 is the major part which is actually monitoring by the mass spectroscopy in wildly. So now we are coming to majorly talk about the iron 57 or now onwards. 57 iron Mossbauer. So our isotope is 57 Fe26. By mistake we read copper 26. So but major issue is that natural awareness. We asked about that. There is a one major problem is that there is a resolution of the Mossbauer spectra is very less because of the uh, gamma y my e value is 10 to the power 4 times lesser than my UVVs. So it is very less resolved spectra than my UVVs. Then at least 10,000 times lesser sensitive than my UVBs by optical spectra. So, but here another problem comes into picture. This is the natural abundance, which is actually near to 2.14%. If we have 100 number of molecules of the iron, in between only 2% are the iron 57. So in that we have to record by with this iron 57 uh, isotopes in the Mossbauer spectrum. And other part is the iron 56. The major isotopes of the iron is iron 56. Ap56, the major isotope found in the nature. So now how we can uh, resolve my spectra? We can resolve the spectra by artificially enhancing the iron 57 into my system. That is the different part. So for that, for now, we are actually need to know we can artificially enhance the abundance of the iron 57. Okay. So now question is how we can generate iron 57 I equals to 3 by 2. We have iron 57 is naturally abundant around 2.14%. But that is the I equals to half. We have the energy. We have the Fe 57 26 I equals to half. We have naturally abundant. So now question is how we can get the I by 3, 3 by 2. How we can get that? We have this is we need the gamma ray. This will be my source and this one will be my sample. I equals to half to I equals to 3 by 2 sample. So now how we can get Fe 57 with the I equals to 3 by 2? How we can get? How to get iron 3 by 2? I equals to 3 by 2. Solve that. This iron I equals to 3 by 2 actually get from the cobalt 57 isotope. From here we can get the Fe 57. Now another question is this is a very radioactive molecule. Radioactive molecule. And how can we make this cobalt 57, Molly? This cobalt 57 can be made by this process, the bombardment of deuterium atom into the cobalt into the iron 56. This is the iron 56, and if we bombard it with the deuterium atom, high energy deuterium atom, we can get cobalt 57, so the 27 plus my 1 neutron, 0 1. And this is actually done in a instrument called cyclotron. Okay, we have a synchrotron instrument. We are making a huge, and we are providing huge magnetic and electric field into it. To there we are enriching the energy of the deuterium, enhancing the energy of the deuterium atom, and then we expose the iron 56 into that over there, and that actually bombard into the atom, the iron atom, and then it's forming the cobalt 57 and 1 neutron. And this cobalt 57, it has a lifetime half-life. The half-life is 270 days. Okay, so we have a cobalt 57. It has a half-life of the 270 days, and but this cobalt 57 has a cobalt 57. This has a I value equals to 7 by 2. So from where how can you get the iron 57 3 by 2? Fe 57 Fe 57 equals to 3 by 2. This is happens how? Now question will be how it's happening. This is actually happen through by electron capture by the nucleus of cobalt 57, and then releasing the gamma ray to gamma ray, and it's forming another iron 57 I equals to 3 by 2. So we have a cobalt 57 27 capture a one electron capture from the surroundings. This electron is not staying into the orbiter, it is going to into the nucleus, and it's neutralize the one proton, and that proton becomes the neutron by the quartz. We have a quartz particle which is actually for forming these neutrons and protons and those things, and from the surroundings. And that quartz particle still forming turns into proton into the neutron, it becomes the iron iron 57, and that is this is I equals to 7 by 2, and that will be my Fe, sorry, Fe 57, this will be my 26, I equals to 5 by 2, not 3 by 2. Still we need to lose its energy to get iron 3 by 2, I equals to 3 by 2, iron 57, I equals to 3 by 2. So for that it's actually decaying another gamma ray to for I equals to 3 by 2, and that is we can write it by the, in terms of the energy term. We have a energy here, this is I equals to 5 by 2 iron 57 Fe 57 57 Fe. Now it's losing its energy to I equals to 3 by 2, and that is also 57 iron. This energy gap, this energy is 136.32 kilo electron volt, and this energy gap is 14.4 kilo electron volt. This energy gap actually 122 kilo electron volt, and it releases a highly energetic gamma ray. So it's release a gamma ray whose energy is 122 kilo electron volt. Now this I equal iron 57 with a I value of 3 by 2 actually again release its energy to make stable I equals to half isotope with a 57 isotope iron. Okay, this is the where this will be my 0 kiloelectron volt, and this will provide the gamma ray which is actually act as a source of my of Mossbauer spectrum, not this one. This one is a highly energetic one. This is actually used as a source of the Mossbauer spectrum, and their energy state change is similar as we are looking for right now for my sample. For the sample, we have the I equals to half iron 57, and then we are this energy gamma ray we are actually providing to the my sample, and that becomes the I equals to 3 by 2. Okay, so now another interesting is that still we have some recoiling over there. Okay, as my vibration is lattice vibration is there, so still will have the recoil, the recoiling, and then how can we improve it to get a proper structure? To that, we are actually using one effect called Doppler effect. We can change the color to get a good spectra. It is called Doppler effect, where we actually change providing some extra energy to the source and to match the energy, exact energy which is required for the sample. So this is Doppler effect we are providing. Let's suppose we have a sample over here that can move by providing Doppler velocity. This is that can be movable. My sample over here, and right. So not the sample. This is the source, and it is actually providing the gamma ray. We have sample over here, which is rigid. We have sample, and we have a detector over here. Here we are getting energy from the here to here. I equals 3 by 2. I y equals to half. This energy transition we are getting, and we need the transition of the I equals to half to I equals to 3 by 2, but we are losing some recoiling energy and we are not properly matched with that. This is my basically source and followed by my this is a source and this is my sample. So we are moving this one towards this direction. We are providing some energy towards this direction. We are getting removing some energy from the gamma ray. So this is the Doppler effect we are providing. Effect we are providing some velocity. Let's suppose from a one particular phenomena here we get some spectra from the with the help of the Doppler velocity. Let's suppose we are initially we have providing some backwards energy that is negative Doppler velocity we are providing. In that case, our spectra looks like. Let's suppose this is my initially my negative one. This is ABS. We are providing my negative Doppler velocity, and now here is my sample in the black color. This is my sample. Okay, so there is no overlap. That means we'll get a zero value. This is my minus v1. Now in a negative direction. Now we are providing another velocity which is actually my red color. Let's suppose it is red color. There is a some overlap over here. This is v2 minus v2. Initially, can write okay. The spectra should be looks like This is called Doppler velocity, and this is percentage of transmittance. Okay, first of all, there is no overlap. That means my spectra will be like this: 0, 100%, 100%, and this will be my 0, 0%. When there is another Doppler negative velocity, which is actually overlapped over here, so we'll get some transmittance over here. Okay, uh, and then we'll have exactly matches with that, exactly matches with the sample 1 with providing some velocity. We'll get the maximum velocity over here, and then we'll similarly we'll have another positive. This is a v3, and we'll have some velocity over here. There will be less, similar to this, and we'll have another one which is not overlap to each other. This is v4, v5. So this is v minus v1 minus v2. This is v3, v4, and we will have 100% v5. So in principle, if we record the on every particular point, then we will definitely get this kind of picture over this kind of spectra for my sample with respect to Doppler velocity, how it looks like. This unit will be my millimeter per second. So that much resolution is required to find below below its below its the each point we cannot get any Mossbauer spectra because of the resolution, because of its resolution effect, or because it is a less resolved spectra than the my UVVs. UVVs works in a nanometer region, so it will be 10 to the minus 10 to 10 to the 4 or less than my nanometer region, so it will be around millimeter per second region. Okay, so that's how we'll get the my spectra. So why this kind of Doppler effect we record? As we can say as source and the sample energy is not, and source energy is not matched or not. So here by moving the source using Doppler effect, we can induce some energy or withdraw some energy from the incident gamma ray. Okay, that that's why, and so that resonance happens. So that resonance happens. Okay, this is the major phenomena. We are actually get why we are need this Doppler velocity to measure my mass spectrum. Okay, if you go to the this some literature, there will be some mass spectrum actually showing to transmittance line, and x-axis is the my Doppler velocity. Okay, just a minute. Now, this is a nucleus phenomenon. As you know, this is a nucleus phenomenon. So how we can actually distinguish its spin state, its electronic spin state, what is the oxidation state? How can I determine by this mass spectroscopy? What is the parameter? Which this is a nucleus phenomenon. We cannot get the electronic electronic. We supposed to not get the electronic behavior of my system. So that is the iron we are talking about. Iron 57. We don't have the idea about the iron 57 electronic. What is the electronic structure of the iron iron center? Check that there is a one other called radial distribution function. In the quantum mechanical term, there is a called radial distribution function. So we have a nucleus surrounding it. There is a electron cloud moving around it, and that electron has a wave function. In that wave function, there is a one part is the radial distribution, and there is the other is the theta and phi, r, theta and phi. The r is the radial distribution we are talking about. For the s orbital is a spherical phenomena. Only the s orbital which have a radial distribution such that where the electron density can be found in the nucleus. These are parameter such that if you plot with respect to distance and the intensity, you will definitely find a one non-zero point at the nucleus for the s orbital. But other p and d orbital or f orbital, they will have zero value at the r equals to 0. This r means distance between nucleus to my electron. So now is the electrons nuclear electron nucleus interaction. Okay, we have some nucleus over here, surrounding it there is electron cloud over there. Electron cloud. That is called radial distribution Bayesian function. Okay, so in the radial distribution function we'll have for electron we have the psi is a wave function. Psi is the wave function. of electron as H psi equals to E psi. That is equals to E psi. Psi is the wave function. This is the psi square value we are talking about. The probability of finding electron density. If we plot the radial distribution function with respect to the radius, with respect to the distance between the nucleus and the electron, this is looks like this is the probability psi square, and we'll have the value of this kind of. This is for 1s orbital. This is the psi, like 1 psi equals to 1s, and then when the r equals to 0, psi square, okay, psi square not equals to 0, and this is the r. And for the 2s and 2p, 2s for this is psi square, this is the 2s, and 2p should be looks like starts from 0 to blue one is the 2p. So this is called node, radial node. So that's why the orbital we are talking about, there is a node. Whenever we are talking about node, 2s has a one node, n minus 1, n equals to where the s we are talking about. Okay, so if 1s is there, then there is no node, n equals to 2 where the 2s, then there will be a one node. For the 3s and 3p, how it looks like? 3s, 3p, and 3d. So let's suppose change the color. We have psi square. For the 3s, we have this is the one node, another node, and then we'll have the major contribution of the my wave function. This is the 3s, and my p orbital will be, there will be one node, but it should start from 0. Its radial distribution is something like this, and then we will have, this is the radial distribution for the 2p, sorry, 3p, and we'll have another, this is for 3d, this is d orbital radial distribution, 3d. So here also we can write s p d, 1s we don't have the 1s, so there should be r equals to 0 to 0, 1s psi square not equals to 0, r equals to 0, 2 psi square not equals to psi square for the every s orbital not equals to 0, psi square equals to 0. There is no r equals to 0, 3 psi square not equals to 0. We have a psi square equals to 0, and here also psi square equals to 0. So that means we have a psi square value is not equals to 0 at the nucleus for the s orbital only. So there is a common space where the nucleus can stay. There is a chances of the some electron cloud can stay into the nucleus. So because of this s orbital has a radial distribution such that there is a non-zero radial distribution into the nucleus. So there is a chances of the some electron cloud can be present my into my nucleus. So this s orbital actually playing a crucial role, that electron density actually playing a crucial role into the nucleus state change. If this electron density is different for each and every particular iron atom, iron 57 atom, let's suppose we have an iron complex of myoglobin, which is completely different than the iron cluster of iron cluster at the what is that iron sulfur protein. There has a different environment, and that electron density distribution is different in a s orbital. And because of that s orbital, electron density is different for each and every particular complex, each and every particular iron atom for different molecule, different molecules. Then there is a electron density distribution different into the nucleus also. This s orbital nucleus, uh, s orbital electron density at the nucleus. So with that phenomena actually getting by the Mossbauer spectrum, we are getting the result from the Mossbauer spectrum, that phenomenon. Okay, so my here is the, we can take home message is the, here is the take home message is the s electron at the s orbital radial distribution is responsible for, okay, for electron nucleus interaction. Electron nucleus interaction. Okay. Now, another interesting thing is that we have some mathematical term over here. We have a nucleus, as you know, we have a nucleus over here. It's surrounded with electron cloud. Let's suppose electron of s orbital. This is spherical in nature. Okay, electron density of s electron density which is present in a s orbital. Okay, and then we have a, this is the called a monopole, and there is a assumption taking a assumption that my nucleus is spherical in nature. Spherical. Second assumption is the radius is, let's suppose radius of the nucleus is r. Then there is an equation called this, my Hamiltonian operator would be looks like equals to 2 by 5 pi, can write it properly, it's not 2 by 5 pi z e square psi 0 square r square. This jd actually can be called as a nuclear charge, and E and mod of psi 0 square called electron density, charge of electron charge density. Electron charge density. Okay, as E contains a minus negative charge, and this is the only the charge of the electron without sign. There is positive because of the proton is there. Z is the number of proton, and the E is because this E is the charge of the electron. It contains a negative sign as the electron is negative, and overall minus E over here. Overall term will be the positive. This is the Hamiltonian operator we are getting. So this is how we are getting. Now if we have a source and the sample over here, we have a source energy. My actual ideal state should, ideal state is the I equals to half, the equals to 3 by 2. This is the ideal scenario. But what we get, this is because of my nucleus and electron interaction. We are getting, this is my nucleus electron interaction. This energy state is changed to a different state, different energy level, and then it's, this is the energy of the source, and which is actually is different in case of sample because of there is different electron cloud outside the my sample. This is also equals to 3 by half I 3 by 2. So this is the E of sample. Okay. So there is another mathematical term is there. This is called delta equals to 4 by 5 z e square r square. It is called delta r by r into psi 0 square of the sample minus psi 0 square of the source. Okay, that means this delta energy difference is mainly E of sample minus E of source. So as my sample has a defined electron density, source has a defined electron density, similarly the nucleus also has defined electron density. So this term will comes into the picture. And in the this delta R is called change of delta R by R is called change of nuclear radius. Okay, change of nuclear radius as my nuclear state change to half to 3 by 2. There is some certain changes over there. So for iron 57, Fe 57, this delta R, this delta R is negative because of R of excited state, that is I equals to 3 by 2, is less than R of ground state, that is I equals to half. But for the iodine 119, this is actually positive. This delta R is positive. Positive. Okay. Now let's talk about my iron electronic distribution. Where my electron last present into that. In a complex form, 57, 26. So in complex form, the electron distribution will be 1s2, 2s2, 2p6, 3s2, 3p6, and 3d10. Sorry, 8. But in atomic form, there is a chances of the 3d6 and 4s2. But atomic form in a gaseous phase, but it is in complex form. In a complex, the iron actually make a complex and make the molecular orbital, where my d orbital is lower in energy and the 4s orbital, 3d orbital lower in energy and 4s orbital higher in energy. But in that case, electron distribution comes to the 3d orbital only. So here outermost electron density, which is actually responsible for the my iron Mossbauer electron density, uh, electron density into the nucleus, that is the only the 3s orbital, not the 4s orbital. Yeah, the 3s orbital is responsible for the electron density, defined electron density. As you know, the penetration power of the outermost electron, inner cell of the this electron distribution is different, and depending on the electron distribution, we can there is a deviation of the electron distribution in each particular complex. So with respect to that, we can actually get a different energy gap value of the sample. That is the delta E, delta value is the energy of the sample is different, and source will be different. With respect to that, we are actually moving the my source such that that can match my energy of the which is required for my sample resonant, and then we'll get a different spectra. That is, with respect to Doppler effect, we'll get a different spectra, and then next day onwards we'll discuss about that. So to that we'll stop over here. Today we actually discussed about, let's summarize all those things. We actually introduce some how my Mossbauer spectra actually comes, my how my source has to be stored, and samples are in matrix form to resolve my vibration recoiling energy, and then comes into the line width and line broadening, why it's required, why is less resolved spectra than the UV spectra. There is a mathematical part over here, and why the all the Mossbauer active elements we discuss about these things. The majorly we are actually looking into the iron 57, and then to get the iron Mossbauer spectra, there will be source. That source is the iron 57, should be iron 57. This iron 57 comes into the cobalt 57 isotopes. That cobalt 57 isotopes, how can I make cobalt 57? There is iron 56. If you bombard it by the deuterium, high energy deuterium, it will form the cobalt 57 and one neutron. And that cobalt 57 actually decay to cobalt, make the cobalt 57 5 by 2. And that cobalt iron 5 by 2, 57 iron 57 5 by 2 I equals to 5 by 2, and that actually decay the gamma ray, which will form the iron 3 by 2. I should iron 3 by iron 57 3 by 2, uh, I equals to 3 by 2 value of the nuclear spin, and nuclear state nuclear spin state value. And then that 3 by 2 actually decay the gamma ray, which is required for the iron 57 excitation from the I by 2, I equals to 1/2 for our sample. And with respect to the Doppler effect, how we actually get the spectra and to change their moving, providing some energy, or uh, taking out of the energy from the source, and providing that particular energy gamma ray into the for the sample which is absorbed, will get a curve, that is transmission curve. We will get that curve, and that is actually depends on the how much energy we are providing. That energy is required by the electron distribution of the my iron center, and further to that, the only the s orbital of the iron, or s orbital of any nuclei, which is actually responsible for the some electron density into the nucleus, that comes from the radial distribution function of my s orbital. And then we found some energy term, that is the delta. This delta is 4 by 5 z square r square by delta r by r, and which is actually sample size square, probability of the electron density of size square, and the source. Depending on that, we can calculate how much energy we are required to move by source. To that, here I'm stop over here. If you need any help, just uh, pin me anywhere in YouTube or anywhere. Okay, bye bye. Now we'll see you in next Saturday. Thank you. Bye.